wherever inelastic collision happens at a certain height from the surface of the earth is called gravitational. The potential energy and kinetic energy of a system, the relative velocities of two bodies after collision. Consider the point A. The body has total energy mgh. Hello students, continuing our session on work, power and energy. Yesterday we established a very important theorem, what we call as work energy theorem, where we proved that work done by a constant force on a body always changes the kinetic energy of the body. And we also learnt something called as conservative and non-conservative forces. We learnt the differences between conservative and non-conservative forces, and finally the properties of conservative and non-conservative forces. In my today's session, I will establish something called as the law of conservation of energy. So, my today's discussion will configure around a very, very important concept called the law of conservation of energy. And I will verify the law of conservation of mechanical energy in the case of a freely falling body. Freely falling body. Now, this is a very, very important question, a very important 5-marker that is asked in the exam. The law of conservation of energy. You might have studied the statement, energy cannot be created nor destroyed, but can be transformed from one form to another. And you might have quoted that as the law of conservation of energy. That is what exactly I will be teaching today. Just upgrading my thought, I will show that the total mechanical energy at any point of a freely falling body always remains the same. So now we formulate the statement, of the law of conservation of energy, saying that total mechanical energy, the total mechanical energy of an isolated system is always constant. Whatever you told that energy cannot be created nor destroyed, I also formulate saying that the total mechanical energy of an isolated system remains constant. Now, what is this total mechanical energy? In simple words, the sum of potential energy and kinetic energy of a system is called total mechanical energy. It is the sum of the potential energy and kinetic energy of a system. Isolated system, a system where there is no interaction with the surroundings. Such a system is called isolated system, and the total mechanical energy of such an isolated system always remains constant. So we have to prove this law, and we are proving this law in the case of a freely falling body, a body or an object that is released from a certain height. It is called freely falling body. Now, I will consider a body A which is placed at a height h from the surface of the ground. Some body, it is placed at this point A. It is placed at a height h from the surface of the ground. Now, let us understand what happens to the energy, total energy of the body at this point A. When it is held at this point A, what happens to its energy? Where we told total energy is the sum of potential energy and kinetic energy. Please to understand, at the point A, the body is at rest. At the point A, the body is not moving. It is simply held at the point A. Now, the total energy of the body at the point A is potential energy plus kinetic energy. Recall the expression for potential energy, mgh. Recall the expression for kinetic energy, half mv square. But very interestingly, at the point A, the body is at rest, which means its velocity is 0. At that point A, the body is at rest, so its velocity is 0, which means it has no kinetic energy at the point A and has only potential energy. So the total energy of the body at the point A is mgh. Very interesting, alva. At the point A, total mechanical energy is potential energy plus kinetic energy. mgh plus half mv square. At the point A, body is at rest. Its velocity is 0. It cannot have kinetic energy, so it simply possesses potential energy, which is mgh. Now let us understand what happens to the energy of the body at the point B. Now, if you observe, the body slowly starts falling down. From the position A, it is released. It slowly starts coming down. Now, it has traveled a distance x from the point A, and its velocity at the point B is Vb. Now, my dear students, as it starts coming down, as it is set into motion, its potential energy goes on decreasing, and on the other hand, its kinetic energy goes on increasing. Now it is set into motion. It is acquiring some speed. So as it reaches the point B, it has lost some amount of potential energy. But on the other hand, it has gained kinetic energy, and from the ground, now it is at a distance of h minus x. Therefore, again, potential energy plus kinetic energy. Now, the potential energy is mgh minus x. The height of the body from the ground now is h minus x. So, potential energy is mgh minus x. Kinetic energy is half mv square. At the point B, its velocity is Vb square. And now I have to calculate this Vb, for which I use one of the equations of motion, V square, A equals U square plus 2AS. initial velocity is 0. Now, the distance at the point B is x. So, VB square is 2gx. So, therefore, substituting in the previous equation, total energy is mgh minus mgx plus half. This 2 and 2 gets cancelled. mgx minus mgx plus mgx gets cancelled. And again at the point B, the total energy is mgh. So very interestingly, at the point A, the body had a total energy mgh, as well as now at the point B, its total energy is mgh. Now finally, from B, it further comes down, it further travels down and reaches the point C, which is nothing but the floor, height h, velocity of the body at C is Vc, and therefore again potential energy plus kinetic energy. Now h is 0, it has reached the ground. No potential energy. So when we substitute, again you can see at C, the total energy is mgh. So very clearly, consider the point A, the body has total energy mgh. At B, the body has energy mgh. At C, mgh, which means at any point of the freely falling body, the energy is conserved. At any point is mgh, and therefore we say the total energy, mechanical energy of a freely falling body is always conserved. Now we study a concept called coefficient of restitution, and we will write an expression for the coefficient of restitution. We told it is defined as a ratio. Coefficient, it should be some number. So coefficient of restitution is defined as a ratio. Ratio of the relative velocity of two bodies after collision. The relative velocities of two bodies after collision to the relative velocity before collision. So, coefficient of restitution is a ratio. Ratio of what? Relative velocity of two bodies after collision to the relative velocities before collision. Now, U1 and U2 are the velocities of two bodies before collision, and V1 and V2 are the velocities after collision. The coefficient of restitution is V1 minus V2 divided by U1 minus U2. Ratio of relative velocities after collision to the relative velocity of the two bodies before collision. Now, again a very important question to distinguish between elastic and inelastic collisions. This is again a very important 3-mark question to distinguish between elastic collision and inelastic collision. Now, a collision in which striking of two bodies, colliding of two bodies, we say the two bodies collide each other. A collision in which both momentum and kinetic energy are conserved. Momentum as well as kinetic energy is conserved. No loss of momentum, no loss of kinetic energy. Such a collision is called elastic collision. Elastic, momentum is conserved as well as kinetic energy is conserved. Whereas collision in which only momentum is conserved, but there is loss of kinetic energy is called inelastic collision. Nodi, it's beautiful agide. If two bodies strike, if two bodies collide with each other such that there is no loss of kinetic energy, no loss of momentum, both kinetic energy and momentum gets conserved, that is called elastic collision. If the collision happens such that only momentum is conserved, but kinetic energy is lost, that is called inelastic collision. Now, forces involved in collision are conservative in elastic collision. Wherever you have elastic collision, the force which brings elastic collision into picture is conservative, whereas forces which bring inelastic collision into picture are non-conservative. So we say, wherever elastic collision happens, conservative forces are seen. Wherever inelastic collision happens, there are non-conservative forces coming into picture. Mechanical energy is not converted into any other forms during elastic collision. Why? There is conservation of momentum and kinetic energy. So need not convert energy into any other form. Whereas in inelastic collision, mechanical energy may be converted in the form of heat. sound, light, etc. So elastic collision, no transformation of energy from one form to another. Whereas inelastic collision, there is conversion of energy into heat energy, light energy, sound energy, etc. This is very important. For perfectly elastic collision, the value of coefficient of restitution is 1. Whereas for perfectly inelastic collision, it is 0. So these are the features of elastic and inelastic collision. And finally, whatever we studied previously, what was potential energy? Yes, it was energy possessed by a body because of its position. Energy possessed by a body because of its configuration. Energy in a spring, energy in an elastic body, the hands of a clock, water stored in a tank. And we told the energy possessed by a body at a certain height from the surface of the earth is called gravitational potential energy. And it is given by the expression mgh. What is its dimensional formula? Mass is m, acceleration due to gravity is LT minus 2L. So m L square T minus 2, and its SI unit is joule. So students, in today's class, we thoroughly understood the law of conservation of energy, the topic of coefficient of restitution, differences between elastic and inelastic collision. The next session, we take up the topic called power. Until then, have a good time. Thank you.